Hello and welcome to LittleBIGPhysics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we examined how quickly Sackboy runs. Today, we'll continue looking at how things move, but this time at non-constant speeds. Here's a classic physics question. An unfortunate sack is in an elevator when the cord holding the elevator breaks. How will the sack move in the elevator? Will he remain in place, float upwards, or be pressed against the floor? We could find that out right now, but let's do some research first to see if we can predict it instead. Let's see what we can find out about how things fall. For today, we'll keep the scenario as simple as possible. Something is falling. It's not moving to the side, there's nothing we can see pushing it up, down, left, or right, and until it begins falling, it was sitting completely still. There are a few questions we could ask. How long does it take for something to reach the ground if it's dropped from a given height? Does the speed of an object change as it falls? What about if different things fall at different speeds? There are simple ways to test each of these questions individually, but I'm feeling ambitious, so let's try to cover more ground at once this time. We're going to try to create a mathematical equation describing how the object falls. This will be a more involved process than usual, both in analysis and designing the experiment, so I'll go through it all slowly. There are a few different things we could potentially measure, like where the object is at any given time, how quickly it's moving, or even how quickly its speed is changing. Fortunately for us, if we can make an equation for any one of these things, we can make an equation for all the others. How? I won't bother with details, but the answer is basically just calculus. Anyways, the easiest of these things to measure is where the object is, since we could just use tag sensors or player sensors to measure distance from some specified point, such as the ground, like we did in the first episode of this series. But how can we make an equation from that? To do so, we need to see how this distance changes over time. Traditionally, to see how something changes over time, we record the different values at different times, and then we can plot that on a graph and create an equation that produces a similar graph. With the right setup though, we can let our tools make a graph for us and work from there. I'll introduce the pieces one at a time. First, think back to the various applications of analog signals. In this case, we'll have a piston receiving an analog signal. The stronger the signal, the further the piston extends. This provides us with a visual representation of the strength of its input. Now let's stick an emitter on the end of that piston. If we emit a small stationary object, like a small hologram block, from that emitter, then the location of that object will represent the strength of the signal at the moment of time it was emitted. Imagine if we emitted these objects at regular intervals, maybe every 0.1 seconds, every tenth of a second, to get as much data as possible, since that's the smallest interval that Little Big Planet will let us use. If the signal is strong at a given moment, then an object will be emitted up high, and if it's weak the next moment, another object will be emitted down below. Of course, this would eventually just end in a straight line of emitted objects along the length of the piston, which wouldn't be very useful. But what if we had the piston moving to the right at a constant speed? Then, all of the objects would be emitted chronologically, in order, from left to right. For example, if the signal started strong and ended weak, there would be emitted objects high up on the left and down low on the right. To make things even easier for ourselves, let's induce this rightward motion with the second piston, this time receiving an analog input from a timer. If the timer is at 0, the second piston is all the way on the left, and if the timer reaches its maximum value, the second piston is all the way on the right. What's great about this is that we can simply tweak the maximum time on the timer to define how long the second piston will take to move all the way from the left to the right. As a final touch, let's give this contraption a nice background. The rolled paper material has regular spacings, so let's use that. If we calibrate the first piston's minimum and maximum lengths so that the minimum length is at the very bottom of the grid and the maximum is at the very top, then we can actually measure the strength of the signal the first piston receives at the moment an object is emitted by looking at where the object is on the grid. If it's 2 spaces up, for example, and the entire grid is 10 spaces tall, then the signal must have been 2/10 of its maximum value, or 0.2, when that object was emitted. This means we can produce a specific quantitative graph using this device. What might we hook up to this device then? Well, we were thinking about using tag sensors and player sensors to detect the location of an object or the player, which we can just connect to this device to create a graph of position against time. Here's a test trial of Sackboy jumping. It's a bit hard to see the points on the graph when everything's so bright, so I dim the lights a little bit while I run the trial. The most interesting part is that the graph actually dips below its starting position as Sackboy lands, suggesting that Sackboy squishes a bit upon impact. That might be interesting to look at in a later video. Now that we have it all hooked up, all we have to do is start the data collection and let the object, that being a blocker Sackboy, fall. We want as much data as possible, so we'll drop things from as high as we can. Now then, what do we see? We find a pretty beautiful curve for one, but let's take a more quantitative approach. I took the time, and quite a lot of time it was, to transpose this graph into Microsoft Excel and try to produce an equation from it. We have to guess what kind of equation this should be though, so let's try out the most common real-life model, constant downwards acceleration. This means that if something falls for, say, 1 second, then it'll be falling twice as fast by the time another second passes. Furthermore, it doesn't matter how heavy the falling object is, or how it's shaped. According to this model, if you drop a feather and a bowling ball side by side, they'll reach the ground at the same time. Strangely enough though, if I just plug in the points and tell Excel to spit out that kind of equation, it gives me an equation, represented by the thin dotted line, that claims that the peak of this curve is about half a second before the trial started. Since the block was completely motionless when we started the trial, that can't be true. If we take it around for a bit to force Excel to make an equation with the peak at the start of a trial, which is a lot harder than it sounds, we run into another problem. The equation's pretty accurate at first, but towards the middle, it overestimates how far the block is from the ground. Then, at the end, it underestimates how high the block is. We can make the graph more steep or less steep, but if we make it steeper, then it'll further underestimate how high up the block is towards the end of the graph. And if we make it less steep, it'll further overestimate the height of the block in the middle of the graph. This unfortunately means that the type of equation we chose won't work for this graph. What kind of equation will work is probably going to be a lot more complicated, and I already have plans to look into it later, but that'll involve a lot more graphs. Fortunately, we don't need to produce an exact mathematical model to answer the question we posed at the beginning of this video. We really just need to know how the elevator will fall compared to how Sackboy will fall. Let's run another trial, this time with Sackboy instead of a block. It's pretty much the same story as the falling block. I tried to generate an equation with constant acceleration just for fun, and it produces the same result as last time. I also tried the same thing with Sackboy falling at a much faster speed, but I had to estimate where the peak should be for the equation that I generated. What's different between the first graph for Sackboy and the graph of the block, however, is that Sackboy reached the ground a bit over half a second sooner than the block did. This further suggests that our attempt to apply the simplified real-world model, where everything accelerates downward at the same rate, was incorrect, since Sackboy and the block fall at different speeds. It does, however, suggest what might happen if we put Sackboy in an elevator and let the elevator fall. Since the block fell more slowly than Sackboy, Sackboy should fall faster than the elevator he's in, or at least he would if the floor wasn't there. Instead, he should just be pressed against the floor. Now that we've done our research and defined our expectations, we can try out the real thing to see how we did. Here's Sackboy in the elevator. Cut the cord, and Sackboy floats upwards instead of being pressed against the floor. Why? Is it because he was inside the elevator rather than beside it or anywhere else? Well, some of you might remember this little mishap that I had with the spring scale in the weight episode. I hate to rely on an anecdote, but this happened off screen and I don't have the opportunity to recreate it. Something similar to this happened when I was preparing to record the episode, but the entire scale shot up to the ceiling instead. Even if Sackboy and the scale didn't necessarily hit the ceiling at the same time, the scale clearly fell more quickly than Sackboy, which also isn't what's happening here with the weight. Where did we go wrong? I have an idea for what we missed myself. I'm sure a lot of you do too, in fact. For now, though, I'll leave it to you to consider our findings on your own, and we'll come back to this topic soon. There are one or two other things I think we should look into before we progress any further as well, so that we can try to avoid missing something like we did this time. So long as we have the patience to piece things together, we should be able to work this out eventually. For the time being though, I'll see you guys next time. Stay curious.